Hello, guys, can you hear me?
Yeah, we can hear you.
Okay, let me wait for 1 minute and then we'll start.
Professor, what's your office hour time?
Monday and Wednesdays, 1:30. Just
And it's also in this Zoom number, right?
what?
And where is in this Zoom number or where is
Oh,
it?
just email me if you want to meet and I'll send you a Zoom link.
I did send an email to you about the homework problem. Could you please saw it?
Yeah, I'll try to reply. Can you send it again? How long ago did you send it?
Last night.
Oh, okay. So yeah, I think I saw it. Yeah, I'll try to reply. I haven't had a chance. Yeah, I see it. You basically said that you did the same thing that they did.
Yeah, and it's always happened.
Right. Well, okay. I think the difference is maybe that you put a vector, you put I, J, and K in a vector. Maybe, I don't know.
But the answer gives the saying they also put the IJK in the vector.
Right. No, they have I, J, and K, but they don't have the brackets they don't start the brackets. So 1 second.
I think what's wrong with that is they put 3/8 and I put 3/8 t. I put the t on beside 8. That's why.
Well, did you start this parenthesis and then do 2i plus 6j?
Yeah.
Right. So this you can't do this.
Oh,
You
I have to do this. If I do without it, it says that's wrong.
Okay, fine. So okay, I'll basically go and I'll just give you credit for it. Okay.
Okay, thanks.
And if it happens with other questions, please let me know. I know archive is not great, so I apologize for that. Okay, so let me begin. We will start with before I begin, if other people sent me questions about homeworks, I think there was one other person maybe at some point that I have not replied to, and I don't reply on time, then just send it again. I have a lot of emails. Sometimes I can't get to everything, but I'll try to answer everything at some point. Okay, so let's continue with the gradient and the directional derivative. So the gradient, and we denote the gradient this upside down delta. It's like an upside down triangle. So it's going to be the upside down. So let's first, sorry, 1 second. Let's start with f of xy. And it's some function, whatever. And then we can take the gradient of f of xy. That's going to be equal to the vector. And in the first component, you take the derivative with respect to x. And in the second component, you take the derivative with respect to y. And that's the gradient. If you have 3 components, x, y, and z, and this would, let's say, be equal to w, and this would be equal to z, then the gradient of f of x, y, z would be equal to f of x, f of y, and f of z. Okay, so by the way, when I point with my stylus, do you see that little, there's like a little thing that's moving around? I've been using it to point at stuff, equations, and I just rewatched a video quickly and I did not see that. So can you see, like, it's a little white thing that moves around? No or yes?
It's the cursor, right, that you're talking about?
I'm talking like let's say I'm putting it on f of a y right now. So do you see like a little white thing moving along f of y or no?
Not really.
No. Okay, so that's a problem. Fine. So I'll try to not use that anymore. I thought you would be able to see it, but okay. So once again, if you have f of x y at some point p p of a b, then the gradient is going to be that delta of fp is equal to f of x at ab, f of y at ab. And for three variables, we'd have something similar. So in the first component, you put f with respect to x, and the second component, you put f with respect to y. Okay. So they ask us, let f of x y be x squared plus y squared. So f of x y is equal to x squared plus y squared. And calculate the gradient and draw several gradient vectors and compute delta f at p where p is equal to 1, 1. So p is equal to 1, 1. Okay, so the gradient of f at xy is going to be in the x direction, we put f with respect to x, and in the y direction, we put f with respect to y. So that's going to be 2x and 2y. Okay, so if we drew this, here's my x, here's my y. So if let's say x is 1, 1, which if sorry, x and y are 1, 1, so this would be 2, 2. So at 1, 1, you would go along the x direction and the y direction to 1, 1, and your gradient will be 2, 2, like that. So it'd be some vector like that. If you went to, let's say, negative 1, negative 1, so that would be going here to negative 1, negative 1, then your gradient is going to be negative 2, negative 2. So you'll be going in this direction. And in general, okay, so let's try negative, so let's try p is equal to negative 1, 1. Then your gradient is going to be negative 2, 2. So negative 1, 1 is negative 1, 1. So it's a point over here. And then negative 2, 2 would be something like, so in the x direction, we're going up 2, but in the, sorry, in the y direction, we're going up 2. In the x direction, we're going negative 2. So it'd be something like that. And in this direction, we'd have something like that. And we will see that, so if I take f of x, y is equal to x squared plus y squared, and I look at this graph, I look at the contours of this. So I try things like this is equal to 1. Well, if that's equal to 1, I get this circle. Or I can try x squared plus y squared is equal to 2. And then I would get this circle over here. And so on and so forth. And we'll see that the gradient of this function, if you look at the contours of this map, again, right? This map has different contours for different numbers, 1, 2, whatever. If you look at the contours, the gradient is always going to be orthogonal to the contours, like this. Here. So because the contours of this map are just different circles, the gradient is just going to be something like this. And then over here we'd have this. Any questions about this so far?
So is gradient different from the slope?
Yeah, so the slope, or it depends what you mean by the slope, but we have in 2 dimensions, we only have slopes in one direction. So f with respect to x will be a slope in the x direction. As you move x, how does z change? Or it would be the slope of the tangent line at that point, as long as you're moving in the x direction. This is not a slope. These are vector fields. So the gradient has 2 components. It has the x component and it has the y component. So these are vectors. And the geometric interpretation between a function and its gradient is that if you take the level curves of the function, which would be these curves over here, then the gradient is orthogonal to them. And we'll talk about why that is soon. But now that we see that, we can interpret the gradient as a vector field. That would be the vector field. It's just a vector field. At every point, we have a vector. And that vector is the gradient. So let's say this point over here might be the point P is equal to, let's say 2, 2. And so then the gradient of f at that point, 2, 2, is going to be equal to 4, 4. Because again, the gradient in this case of xy is equal to 2x, 2y. Is that clear?
Okay, yeah, thank you.
Okay. So here we have part of that picture. Okay, so now they say gradient in 3 variables. They want, so f of x, y, z is z e to the 2x plus 3y. F of x, y plus z is equal to z e to the 2x plus 2y, 3y. And they want us to calculate this. They want us to calculate the gradient at 2, -3, and 4. So they want us to calculate the gradient of f at 2, -3, and 4. Okay, so the gradient of f at x, y, and z is going to be equal to, so would have f with respect to x, f with respect to y, and f with respect to z, which is going to be equal to, so f with respect to x is z e to the 2x plus 3y times 2. F with respect to y will be z e to the 2x plus 3y times 3. And f with respect to z is just going to be e 2x plus 3y. And so now the gradient of f at 2, -3, and 4 is going to be equal to 4e to the 4 plus or minus 9 times 2, 4e to the 4 minus 9 times 3, and e to the 4 minus 9. So this is going to be our gradient. Any questions about that? Okay. So, one second. Oh, maybe I did not. Did I do -2? 1 second. Oh, I think I plugged in these numbers incorrectly. 3, -2, and 4, and I did 2, -3, and 4. But I'm just going to keep it this way. I'm not going to put in the other numbers. So this is not exactly the answer to that question, just because that I wrote these numbers incorrectly. So if you want to do that problem, you can try it. Okay. So properties of the gradient. So the gradient is it distributes over addition. So you can just put it in and get gradient with respect to x, f, gradient with respect to y, gradient of f, gradient of y. It distributes into the constant. We have the product rule of the gradient. The gradient of fg is equal to f gradient g plus g gradient f. All this, by the way, comes from the definition of derivatives. And then we have the chain rule for gradients. Okay. I would say you don't really need to know these. So I've never actually used these. And if you need to, you would be able to probably figure it out. But I mean, the main reason why is because you can just ignore that. And let's just do an example over here. So over here, we're going to have an example. G of x, y, z is equal to this thing. And they want us to find the gradient of it. One second. Yeah. So g of x, y, z. G of x, y, z is equal to x squared plus y squared plus z squared, x squared plus y squared plus z squared to the 8th. So the gradient of g at x, y, z is going to be equal partial of g with respect to x, partial of g with respect to y, partial of g with respect to z, which is going to be equal to, and now the 8 comes down, so you have 8x squared plus y squared plus z squared to the 7th power times 2x. And you, in the y component, you're going to have 8x squared plus y squared plus z squared to the 7 times 2y. And then the z component, you're going to have 8x squared plus y squared plus z squared, 7 times 2z. And this again would be your gradient. Any questions about this? Okay. Let me see. So I think we're gonna skip this and move on to directional derivatives. Let me actually see how long this chapter is. Okay. We have 2 days to do this chapter. So I think I'm gonna continue with directional derivatives, and then I'm gonna stop at the properties of the gradient. So directional derivative is this. So far, what we've done is if we have a surface and we want to find the derivative in a simple direction, like we want to fix y, move along x. So this would be our partial with respect to x, and see how that affects our z, partial with respect to z. And partial with respect to z over partial with respect to x was, we said, f with respect to x. And so this would be the derivative in the x direction as you move in the x direction. And we also did something similar in the y direction. We said, oh, we can move in the y direction. So this would be partial with respect to y. And then we would have that the f of y with respect to y is going to be partial of z with respect to y. But we would also like to not have to move in the x or y direction completely, but move along a vector. And so this would have some amount that you're moving in the x direction, plus some amount that you're moving in the y direction. And we want to know how the partial with respect to z changes. So that's, we're moving along a vector. So we would, in the xy plane, we would be moving like this, let's say. Instead of moving only in the y direction, x direction, or only in the y direction, we want to move in some direction of a vector. And we want to be able to compute the derivative of that. So that is the directional derivative. Okay. And when we do that, we will have as the definition the directional derivative with respect to at f of f at p. So that would be the directional derivative in the direction of u. So u is your vector. So u is this vector. This is our vector u of f at the point p. And in terms of the definition of the limit, we can write this as the limit as t goes to 0 of f of x plus h t comma y plus kt minus f of x comma y over t. That's just the that would just be using the definition. Although, one second, this would be at the point. So this is when this p over here is equal to xy. So it's not a point, it's anything. If it were a, b, you would just put a here, b there, a here, b here. Okay. So, in general, we would say that to compute it, forgetting about the definition for a second, to actually compute it, the directional derivative in the direction u of f at p is going to be equal to the gradient of f at p dotted with u, provided that u is the unit vector. It's always very important to turn u into the unit vector. So then this would be the directional derivative. But again, if you're told find the directional derivative in the direction of some u, so let's say this is it, and here's your u, and they tell you find the directional derivative in the direction of this u, you have to turn this u into a unit vector if you are going to use this formula. So you take this u, you take u over the magnitude of u. Let's call this thing u prime. And then this point over here, let's say, is p, point p. This is a point p. And then the directional derivative of u, the directional derivative in the direction u of f at p is going to be the gradient of f at p dotted with u prime in this case, because again, we're looking for the unit vector. Any questions about this? Okay. So they say if f is differentiable p and u is a unit vector, then the directional derivative in the direction of u is given by this formula. Okay. So here's an example. Let's say f of xy is x e to the y. So f of xy is equal to x e to the y. And p is equal to 2, -1. So p is equal to 2, -1. And v is equal to 2, 3. V is equal to 2, 3. And they say calculate the directional derivative in the direction of v. So the first thing is to turn V into a unit vector. So let's do that. Let's take U is equal to V over the magnitude of V, which is going to be equal to 2 comma 3 over the square root of 4 plus 9, which is going to be equal to 2 over the square root of 13 comma 3 over the square root of 13. So in essence, what we've done so far is here's my x, here's my y. They gave me a v, here's my v. It's the vector 2 comma 3. And I turned it into a unit vector. So this is the vector u, sorry, v. And this over here is the vector u. And now that I have the vector u, I can calculate my directional derivative. The directional derivative of f in the direction of u at the point 2, -1 is equal to the gradient at the point 2, -1 dotted with my u, which is 2 comma 3, and 2 over the square root of 13, 3 over the square root of 13. So let me continue down here. Okay, so what is the what is the gradient of f at 2, -1? That's going to be equal to f with respect to x at 2, -1, and f with respect to y at 2, -1, which is going to be equal to, so f with respect to x is e to the y. So that's e, and my y is -1 to the -1. F with respect to y is going to be x e to the y, and that would be 2 e to the -1. This is my gradient. And so then the directional derivative in the direction of u, f at -2, 1. Sorry, maybe, yeah. 2, -1. Yeah, is going to be e to the -1 comma 2 e to the -1 dotted with 2 over the square root of 13 comma 3 over the square root of 13, which is going to be equal to 2 over the square root of 13 e to the -1 plus 2 e to the -1 times 3 over the square root of 13. Any questions about this?
So now this is slope, right?
Yeah, this would be the slope in the direction of u. So it's a number, and as you vary your position in the direction of the u, as you move along, back and forth along u, the z changes in this way. It's proportional to that. So yeah, it's the slope. Okay. So then they do another example, but I'm not going to go through that. It's just same exact thing, finding the unit vector of v, taking the gradient of this f. Again, yeah, finding the unit vector, dotting them, and you are done. Okay. So some properties. Oh, 1 second. Yeah, I'm gonna Let me just see how long this is. So I'm going to continue with this next time. And if there aren't any questions, I'm going to stop here. So we got up to properties of the gradient. Any questions about any of this? Okay, then if there are no questions, we will stop here. Have a nice day.